Hi, guys. How you guys doing today?
Not bad. How about you?
Good, thank you. I like the warmer weather, although I hear it's supposed to snow next week. Yeah, it's really nice outside, isn't it? Alrighty. Okay, so while we're waiting for everybody else to show up, I just want to remind you guys about what's coming due. So let's see, tomorrow we have a quiz 5354 primarily, and then we go back to the 4645 questions. There's some questions in 5.4 at the end that are like these two. You guys will notice on our homeworks that I actually posted a new homework assignment that said, go back and complete 4.5 and 4.6, which is like do the endpoint checks on them. And so the questions that you really need to focus on, give me just a sec, the questions you really need to focus on are 13, 14, 16, and 17. If you look, and I just compared these just to be sure, they are the exact same power series. So question 13 on 4.5, question 13 on 4.5 is the same power series as question 13 on 4.6. So take your answer from 4.5 because you've already done all the work, right? So 4.5 is about, we found the radius and center of convergence, okay? And then we came up with the possibilities for about I'm sorry, I'm getting distracted by a question. So we found that the possible interval values, well, what you need to do for 4.5 for that power series is go back and find the exact interval. So does it include, does it not include? We're going to do all these endpoint checks today. We're going to learn how to do that. 4.6, you're taking that function, that polynomial, you're taking the derivative. You're taking the derivative and the integral, and what you want to do, you have to find the radius and center of convergence. They're the same as what you found in chapter 4.5, they should be. But now what you want to do is you need to go recheck your interval bounds because the interval bounds are going to change, okay? Because now after 5.4, you will have learned how to do it, right? So just in summary, in words, right? So they're the same problems. So in chapter 4.5, you find the interval on the polynomial on P of X. In chapter 4.6, you see how the interval endpoints may change, not the numbers, but whether they're included or not, okay? Like whether you have square brackets or round parentheses on our intervals when you take the derivative and the integral, okay? So that's stuff for 4.5 and 4.6. I was unsure about 3.1 in Appendix A, and I really want to make sure that you guys have this stuff, this knowledge on how to do these things. So we're going to finish up 5.4 today. We're going to go back over, excuse me, 4.6 and then 4.5. In my 9 o'clock class, we did not get through all of the examples for 4.6, so we're going to continue that tomorrow. And I'm debating, I think I may actually start 3.1 on Monday so that you guys kind of have a clear mental break on things, because 3.1 is a completely different topic. It's basically applications of integration. So I want to make sure that we really kind of nail this stuff home because it's really a big takeaway for the semester for what we're trying to teach you in calculus too. So let's make sure I'm okay with spending that time. We have the time to be able to spend on that this semester. So coming down the pipeline. Let's see, you guys asked, or one of you asked, when do we expect to have the midterms graded? Yeah, I'm in the process of grading them. Thank you for your patience. It takes forever to grade online tests. I'm hoping by this weekend I'll have them all graded and posted. So I'm working through that. Actually, that reminded me, I want to talk really briefly about the quiz because I started taking a look at the quiz and I just want to kind of talk about strategies because I saw similar problems on the quiz questions. So let's do this. All right, so on the quiz, this is our quiz here. When you guys see this, I tried to drop a hint with, even though this is in bracket, I've got a parentheses plus a parentheses so that you can think that you've actually got two separate series types that you're going to be working with. I'll scan this in and post it, but I just want to make sure we're all on the same page about it. Hang on a sec, let me try these here. Does that help? No. Okay, so right, we broke this up into two separate series types. And so that means that I have to check the convergence on each one. This is a telescoping, okay? which means you can enumerate out and just to confirm to yourself that this first term 1 over k squared forms the first term that doesn't cancel. Okay, and then so basically I'm looking at the limit of this term right here, 1 over k plus 1 squared. That goes to 0, so then I can say that the telescoping series is gonna converge, and then my sum is gonna be the first term minus this limit right here, okay? So that's gonna equal to 1. This is a geometric series, okay? This here, once I bring the -1 in with the 4, because they have the same k, basically get my r is equal to -1/4, my a is equal to 3, so this satisfies our criteria for convergence on a geometric series. Okay, so because that converges, right, then I can calculate the sum on my geometric series. So now I've got, let's see, my sum's going to end up being, after I do all the work, the sum's going to be equal to -3/5 on that one. I put the two sums together and I get 2/5. Okay, so I saw some of you kind of trying a whole bunch of different things. So you're going to lose points if you don't tell me what series test or series type you are working with. You're going to lose points if you don't tell me the criteria for convergence or divergence of that and where this series falls. Like, what's the criteria? Does it satisfy that or not? And then what's your conclusion? In this case, we were asked to state the sum. And so we did. We did state the sum. Now, be careful. It doesn't converge to 2/5. This is what it sums to. Okay, so this is a summation. What it converges to may be different. We only check to see if it converges, and then if it's possible, we'll sum it. Question 2. So what I saw in question 2 was this is, you can do an nth term test, which I guess technically speaking leads you to an indeterminate, which means that I can end up doing a comparison test with a similar series 2k over k plus 1, which is the nth term test. This is going to diverge. This is smaller, so it pushes this up into divergence too. Probably your best bet is to do a ratio test. Okay, this goes to infinity, which is greater than 1, therefore it diverges. Okay, this bonus problem, I put it as a bonus. I thought it might be a little complex for a quiz problem, but I wanted you guys to see it. So please, if you didn't try, if you just kind of skipped it, please try it to take a look at it. So the bonus problem tests your knowledge of also how do the exponents play with each other, and then after you get the exponents simplified, what kind of a series are you looking at? So 3 to the n plus 1 is 3 to the n times 3 to the 1. 2 to the n minus 2 is 2 to the n times 2 to the minus 2. Well, 2 to the minus 2, when it's 1 over 2 to the minus 2, that's equal to 1 over 4, which is 1 over 4. So this is equal to 4, right? And so now this 3 to the 1 times 4 gives me my value, which is equal to 12. And what I'm left over is I've got 2 to the 2 times n, which is 2 squared raised to the nth power. So it's 4 to the n. So I have 3 to the n over 4 to the n, which is really 3/4 to the n times 12. Okay, so once we simplified all the exponents, we're dealing with a geometric series. And the rest is straightforward, right? So I've got my a, I've got my r, it satisfies for convergence, and then I can calculate the sum. And because this is starting at 0, I don't need to subtract the 0th component, the 0th term. Like I did on part 1, question 1, when I calculated my sum, I had to subtract out my 0th term because my summation started at 1. Okay, so please, make sure you're reading your series to make sure that you remember k equals 1, k equals 0. Where are we starting at? Okay. All right, so that's the quiz. I'll scan that in and put that up later so you guys can see that. Okay. Phew, has a lot to take in here. We've got a lot of stuff going on, but we're going to work through it piece by piece, so we should be good. All right, so last time we left off, I'm at chapter 5.4. These are my, let's see here. Let's see if I can get this exactly here. All right, so we're dealing with, we've got an n factorial. We said this was a good candidate for our ratio test. This is where we left off. Okay, so we were going to do one more example on our ratio test. I'll tell you what's a ratio test. And the question is, how do I know I want to use the ratio test? It's because I've got an n factorial. So with the n factorial, it's a good candidate for the ratio test. Okay, because the ratio test will help me basically clean up my factorial. So let's try the ratio test. Okay, so remember our ratio test. I'm going to take the limit as n goes to infinity, absolute value. So the absolute value is going to knock off that -1. So I'm going to get n plus 1 factorial 1000 to the n plus 1 all over n factorial 1000 to the n absolute value. So this is a test for absolute convergence because I've got an absolute value going on here. So this is, I'm going to multiply by its reciprocal. So let's clean it up. We'll group like terms. So I'm going to get n plus 1 factorial all over n factorial times 1000 to the n, 1000 to the n plus 1 here. So what are we dealing with here? Our factorials simplify. So we're dealing with essentially n plus 1 times this 1000 to the n over 1000 to the n plus 1 is 1 over 1000. Okay, but this, as n goes to infinity, this thing goes to infinity, which is greater than 1. So therefore, this thing diverges. Okay, and I'm going to say diverges by the ratio test. Okay, I have to say what test I'm using and the criteria for its divergence or convergence. Okay. All right, so let's go back to our notes for a second, and I'm going to talk about a different series test. This is our last series test. This is also a theorem like everything else. This is called the root test. Okay, and so the root test is going to work well. Works well when we have a series with an nth power, like an exponent that's an n, like 1000 to the n or something, or like some equation raised to the nth power. But we should also say that, but this is always inconclusive with a p-series. So if you try to apply the root test to a p-series test, you're going to get something that's, your answer is going to be inconclusive. Okay, so make sure that you're identifying like which series type you should be doing and using that correctly. So which is part of actually what we're going to talk about after we summarize this. Let me write down what our root test is. So my first criteria, the limit as n goes to infinity, I'm taking the nth root. I take the absolute value of my series a sub n. If that's less than 1, then our series converges, and it's going to converge absolutely. All right, because I have an absolute value here, so this is a test for absolute convergence. Let's see if that's a little bit better. Seems like I can see that a little bit better. So converges absolutely. The next one, our root test criteria. I take the nth root. This is greater than 1, then my series diverges. It doesn't diverge absolutely, it just diverges. Okay, so this is a test for convergence and divergence, right? So some tests are tests for convergence only, some are for divergence only, and some are for both. Okay, so it's a test for both, but it has an inconclusive part. If it fails the root test because it's inconclusive, right, then you should probably try a comparison test or something else. All right, so let's try some examples so you can see how we would apply this and what it would look like. All right. Let you guys finish writing that and then we'll do examples. Okay, so example number 9. This is a series converge or diverge, which test to be used. So look, something, something, something raised to the nth power, right? So this is an nth power. Maybe I should use the root test. Okay, so that's a good criteria for my root test. So now what I'm going to say is I'm going to go the limit as n goes to infinity, the nth root of n over 2n plus 3 oops, to the nth power, and I'm taking the absolute value of that. We're okay either way, but let's go ahead and do this, right? So when I do this, after I take the nth root of it, what I get is limit as n goes to infinity of n to n plus 3, right? You should be thinking, if I take the nth root, is it going to make it more simple? Okay, so look what it does. It kind of gets it out of that context. So now I can just evaluate this, right? So this is n over 2n, which means my highest degree terms are the ones that are going to be interacting. So I'm looking at my coefficients here. Coefficients of my highest degree terms. So I'm looking at 1 over 2. So this thing goes down to 1/2, which was our criteria for convergence and divergence, right? Converges, absolutely. I'm going to write down by the root test. Okay. All right. This one, e to the 2n all over n to the n. You can kind of think, if you're not quite sure, it's like e squared, right? Raised to the nth power all over n to the n, which I can kind of also write as 1 to infinity e squared all over n raised to the nth power, right? So this is raised to the nth power. So I'm going to think I'm going to do my root test. So I'm going to go limit as n goes, let's try root test. Somewhere I have to say what test I'm using. So limit, you take the absolute value, e to the 2n all over n to the n, right? And now let's do this. Whenever we take a square root or a third root or a cube root or whatever, right, we're basically raising this argument here to the 1 over n power. So this is like saying n to infinity. I'm going to go e to the 2n divided by n all over, oops, sorry, n to the n divided by n, which is kind of like what we would have seen if we had done it here. Limit as n goes to infinity of e to the 2 all over n to the 1. As n goes to infinity, this e squared is just a number, right? This just becomes equal to 0, right? Which is less than 1. Therefore, this thing converges. And I'm going to write down by root test. I'm going to be good about saying which test I used when I say what my conclusion is, convergence or divergence. One thing to note here, I'll write this in a different color, is that we could have also done the ratio test on this. Could have also used ratio test. It would have showed convergence, but it would have been much more messy. It would have worked too, but you would have had a lot more algebra to take care of, a lot more things to clean up. So your sort of your goal when you're doing these things is to try to figure out like what are the tests that I can work with, and what's the best option? Like, what should I use for that? All right, so I'll scan in these lecture examples later, and I'll post them so you guys can have them. So one thing I want to talk about really quick is, right, we've got our blank page here, and I really want to encourage you to fill this out. Your test name, an example of what the series would look like. If you have a test that only shows divergence, then put an extra the convergence to remember for yourself that this thing doesn't tell me anything about convergence. If it's only for convergence, then put an extra the divergence so that you don't get confused and think, oh, can I do divergence on this? So let's write down, I think we've got like 9 or 10 different tests. So let's write down what are our different tests. Series tests, right? Normally, when I teach this in class, I have you tell me what those tests are, but it's harder to do online, so we'll just talk about them here. So we've got our nth term test, okay? That's, I'm not,
Professor,
yeah, what's up?
could you please scroll up? I was copying the root test conditions.
Okay.
Just for a minute, thank you.
You're welcome. These are in no particular order, then I'm going to write down the different series tests. So, you know, if you already have your table, you could just check to make sure that you're getting all the series tests. Let me know when you're all set.
I'm all set.
Okay, great. All right. So different series tests. We have the nth term test, right? We have our geometric series. We have telescoping series. You have all of these in your notes. They're also all in the videos that we posted on our Canvas page, okay? Plus also on the YouTube page. But this, we were just putting them in a list so you can look through your notes for them. We have the P series. We have the alternating series. We have the integral test. Okay. We have the root test. We have the ratio test. We have the direct comparison. And then we have the limit comparison. Okay, you maybe even want to do like show, like extend this table out and give an example of convergent and divergent for each of these series types, just to help you start to make sure that you really understand what do these series look like. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different series. So maybe on like extend it for the paper and then do an example of divergent and then an example of convergent on your table or something like that, or do a extend, like put a piece of paper on the side with a divergent and convergent example, and then that way you can kind of get a feeling for what do these things look like. All right, what I want to do when we go as a way of summarizing all the different series tests is let's talk about kind of like a decision tree or a strategy or a flow chart, depending on your major, how you think about things, like how we know what series tests to use and how we should analyze this stuff. So I'll just write down, so at the top, we're going to talk about strategies for testing series, right? And basically we can kind of subtitle this, how to choose an appropriate test. Okay, so we're going to look for some guidelines on testing for convergence or divergence. So the first thing that you want to ask yourself is, the very first thing is, does the nth term test work? Does the nth term test, let's see, does not equal to 0. So if the nth term test is not equal to 0, good, then it diverges. Okay, if it equals 0, it's inconclusive, you got to use another test. But this can be a really good first test when you're given a series. You do a quick check, it's equal to 1. All right, I need to do a different series test. But if it's equal to 0, you have to do a different series test. But if it's not equal to 0, now you've satisfied your nth term test for divergence and you're good. You've just shown how, what does this series do? Okay, so that's a good first strategy, checking your nth term. Okay. The second strategy is our series one of our special types? What do we mean by special types? They have special forms, and we're talking about geometric, telescoping, P series, alternating series. Right, so these are all very specific types of series, right? They have, and once you've identified them as this series type, they have a very specific test that you can do to see if it converges or diverges. Okay, so check to see if it's one of those special types, because if it is, then use the series test that's associated with that. It'll be more straightforward. Okay, can we do one of these tests, the integral test? Right, we're going to talk about in a minute, integral test, root test, a ratio test. right? So for the integral test, what do we need? We need to make sure that my f of n is like an f of x, and I can take the integral of f of x, right? So if I look at my series, it looks like it could be a function, right? If I can represent it as a function, can I integrate that function? If I can, I should do the integral test. Root test, we're looking at, I've got something raised to the nth power. If it's raised to the nth power, doing the root test is going to get rid of that, which is going to make evaluation that much easier. Ratio test, I usually look for a factorial. Something, somewhere. You know, if I've got a factorial, then the ratio test is usually what I apply. Okay, so these are like your strategies, things that you're looking for. All right, lastly, so like if this one doesn't work, I check here. If this one doesn't work, I check here. If all of these things, if I can't really apply all of these things, then I do a comparison. In a comparison test, when I do a comparison test, I ask myself, can the series be favorably compared with a known simpler series, like a P series or geometric series or something like that. And then I can check to see, I can do a limit comparison, or which is what I like, or a direct comparison, which totally works too. Okay, so you're going to do, this would mean limit or direct comparison. They have different criteria, which you can look up in your notes, you know, to make sure that you have that clear. All right, so let's do some like, we're gonna do some speed series analysis, like speed chess. We're gonna do some speed series analysis on, you know, we're gonna write down a quick series example. This isn't in any lecture examples. This is just quick example. What should we do? So I've got n equals 1 to infinity, n plus 1 all over 3n plus 1. So let's follow our own advice. So can I do the nth term test? If I do the nth term test, as n goes to infinity, I get 1/3 that's not equal to 0. So therefore, this thing diverges by the nth term test. Right? I'm not actually going to do the series test. I'm just telling you, like, given this series, like, how would I evaluate it? Our second example, got pi over 6 raised to the nth power. Don't be confused. Pi over 6 is just a number, right? Raised to the nth power. So it's raised to the nth power. It looks like one of our special types, the geometric series, right? So we're looking at r is equal to pi over 6, which means, right? So this is true. So therefore, this thing converges. Okay. I'm not calculating. I'm not doing all the details like the sum or anything else like that. So our third example, n equals 1 to infinity, n e to the minus n squared. Right, when I do this one, you know, the nth term test, oh, it doesn't look good. It's not any one of my specific types, but my f of n, I can write this as a function x e to the minus x squared, which I can integrate that, right? So if I integrate f of x dx exists by substitution, I can do this. I can integrate that, which means I can calculate this out as, you know, an improper integral and figure out if this thing's going to converge. Okay, and I'll just tell you, you can do this out on your own, but this will converge by the integral test. Okay, n equals 1 to infinity, 1 over 3n plus 1. Okay, so I can do the nth term test on this. This is going to go to 0, though. Nth term test doesn't work. But what I can do is I can do a comparison test, and I'm going to check it with, say, 1 over 3n, which is 1 over 3 times 1 over n. So this is a coefficient, right? Some, you know, scalar multiple of a divergent p series, right? Which diverges because p equals 1. That's this one right here. Okay, so if I compare it to a divergent p series, right? I like to do the limit comparison. And I'm going to show that both series diverge by the limit comparison. Right, so we're doing speed chess here, but we're talking about like, you know, how are we going to be evaluating, you know, our different series. So we're going through it quickly in our mind, but see how we're processing these decisions, right? Because I like the nth term test, but often it's inconclusive, right? 1/3n plus 1, you know, I mean, that goes to 0, right? So that doesn't help me with the nth term test. All right, so next one, n equals 1 to infinity. I've got -1 to the n, 3/4n plus 1. Okay, so this -1 to the n, I love it when I see that. Why? Because that means it's an alternating series. And I can do the alternating series test on it, right? And so when I do the alternating series test, I'm not going to do it out, but it's going to converge. Okay, you can do the individual tests on these. I'm just showing you our decision process for which test we're going to be using. N equals 1 to infinity. N factorial all over 10 to the n. I've got a factorial, right? And plus my nth term test, right? Well, I've got a factor. I think the factorial goes to infinity before this one does. But I can also do my nth term test on this one. Nth term test, except that I've got, oh, sorry, this gives me infinity over infinity. So then I'm going to use the ratio test because I also have the n factorial. Okay, so this is, right, it's not something that I can take the derivative of easily because n factorial is a discrete function, right? So, so I can do this, and the ratio test is actually going to show it's going to diverge. We also know it's going to diverge because I think we showed before, we stated before that n factorial goes to infinity before the exponential functions do. But it's better to just use your ratio test for that. All right, n equals 1 to infinity. This one, n plus 1 to n plus 1 to the n. Oh, look what I have. I have an nth power. Okay, so I'm going to use the nth power. Means it's a good candidate for our root test. Okay, which we're going to show that this series from this is going to converge. Okay, and then this is an absolute convergence test, so you'll be able to tell that from here. Okay, so we just did a speed analysis of like 7 different series. Okay, we didn't go through it all in detail, but we're just, you know, kind of asking ourselves these questions. Could an oscillating series be compared to its non-oscillating counterpart? So an oscillating series is going to be, it depends on what it is. So if it's like -1 plus 1, -1 plus 1, -1 plus 1, then I would essentially take the nth term test and say that's not equal to 0 and then call it a day, say it diverges. But something like -1 to the n all over p to the 4, you don't have to, it's an alternating series test. So if I do that one, I don't need to do any kind of like a, you know, if I do like a direct comparison or a limit comparison, I don't use absolute values on that. So now I'm comparing an alternating series to like a 1 over p to the n. And so what I want to do is I want to be very careful. So that's an alternating series. So I'm going to use an alternating series test. Okay. All right. So those are all of our series types. And those are the strategies that we would use to help us navigate through figuring that out. So what I'm going to do now is I've got my notes, my lecture examples for 4.5, right? So I pulled out my old lecture examples for 4.5. So we're going back to power series now, right? So the power series that we want to take a look at, let's see. Sorry, right here. So 4.5, right? So we've got example 4 is the one I'm going to start with because the other ones we weren't looking for an interval of convergence. So I'm looking at this one here. So what are the radius and interval of convergence? So we already went through, this is our power series. So this is a polynomial, right? So we used our ratio test to figure out what's our radius. So on example number 4, we found our radius was equal to 1 and our center is at 2. Which means our interval of convergence is center plus or minus radius. So our our interval is going to be from 1 to 3, 2 minus 1 to 2 plus 1. So now what I have to do is an endpoint check. Okay, so we're basically going to be doing endpoint checks on all of these here. Give me just a second, I've got papers flying around. Okay. So my endpoint check. So the endpoint check means I have to check my values. So I'm going to go from, oops, sorry, I'm going to go from 1 to 3. So I have to check x is equal to 1 and then x is equal to 3. So for that x, I'm going back to my original power series, right? 3 times x minus 2 raised to the nth power. I plug in each of those endpoints into this power series and I'm left with just a regular series. I see if my series converges or diverges at that x value. All right, so let's go ahead and do it. So if x equals 1, I'm going to rewrite this. So this is going to look like n equals, would we start off at 0 to infinity, and I'm going to go 3 times 1 minus 2 to the n. So wherever I saw my x, I plugged in a 1. This is my plugging in those endpoints. Okay, so what this comes down to is n equals 0, 3 times 1 minus 2. This is minus 1 to the n. Okay, so this is this is an alternating series, right? I've got I'm going to look at so positive 3 minus 3, positive 3 minus 3, positive 3 minus 3. But what happens is when I go the limit as n goes to infinity of 3 to the minus 1 of n, or even just of 3, I don't even deal with this part. This does not equal to 0. Okay, which is my nth term test, right? Which means this diverges. Okay, so because my series diverges when x equals 1, 1 is not included in my endpoint. Oops. So let's scroll up. We're going to do x equals 3. Okay, so I'm going to do the same thing. So n equals 0 to infinity, 3 times 3 minus 2 to the n. So wherever I had my x in my power series, I plug in this x equals 3. Okay, so what do we get? We're going to get 3 times 1 to the n, which is just simply, I'm going to sum up 3. So 3, I'm going to add 3 an infinite number of times. I can do the nth term test on this one too. So the limit as n goes to infinity of 3 does not equal to 0. Therefore, this thing diverges. So 3 is not included in the bounds on my endpoint either. Okay, so that's our endpoint check. We had to do that for both x values, for both values of our endpoint, 1 and 3. Let you guys finish writing that, and then we'll do the next example. All right. So example 5. Right, so we're going back over our endpoints now. So we've got, sorry, example 5 looks like some x to the n all over n. So we did our ratio test last time. We found that the radius was equal to 1, the center is at 0, so our interval is -1 to +1. So we have to do an endpoint check to see what's included. We already said last time I gave you the answer, but now I get to find out why. So when x is equal to 1, right, I'm going to check this here. When x is equal to 1, everywhere I see an x, I plug in a 1. 1 to the n all over n. This is equal to 1 all over n. We recognize this now, right? This is a p series. P is equal to 1, therefore this diverges. Okay, so our interval, +1, is not included, right? So this round bracket, right, means it's not included in my endpoint. X is equal to -1, n equals 1 to infinity, -1 to the n all over n. This is our alternating series. This is the alternating harmonic. Okay, so I have to check limit as n goes to infinity, 1 over n, that's equal to 0. My second criteria, that's here, so this thing converges. So my endpoint, my endpoint check revealed my interval was this. Okay, -1 is included, +1 is not. The numbers are the same, right? as what we found before. That's the center plus or minus our radius. Remember, if your radius is equal to 0, you don't do an endpoint check. That's just a point convergence. If your radius is infinite, so all values of x will converge, you don't do an endpoint check either. We'll ask you for endpoint checks on things, right? If you've got some kind of values there. Actually, we won't tell you to do the endpoint check. We'll just assume that you're going to do it. All right. So example 6. Right, so remember where we were. Example 6 looks like this. Okay, we want to know what's the interval of convergence and the radius of convergence. Okay, so from last time, what we found out from our ratio test was our radius was 2 and our center is -1. So -1 minus 2, -1 plus 2 gives us our numbers for our endpoints. Right, so I'm going to check different values. So I'm going to check the first. It doesn't matter what values you check first because you're going to do them both. So when x is equal to -3, I take my series -1 to the n. My x is now the variable in operation. This is the one that we're working on. So when x equals -3, so everywhere I see an x, I plug in -3. So this is going to simplify down to -1 to the n. -3 plus 1 is -2 to the n over 2 to the n. So this is like -1 to the n times -1 to the n times 2 to the n all over 2 to the n. Right? The 2 to the n's cancel. This just becomes +1. This is really like we're just summing up 1. Right? So I'm going to sum 1 plus 1 plus 1 plus 1 an infinite number of times. You get the idea. I can do the nth term test. Does not equal to 0. This thing diverges. Okay, so my interval at x equals -3. This thing is not going to include -3. X is equal to +1. Let's try that and see what happens. So the same thing. So wherever I see x, I'm going to plug in +1. Okay, so what are we dealing with? We've got -1 to the n. Oops, so this is an n. 2 to the n all over 2 to the n, which is equal to -1 to the n. So I'm going to go -1 plus 1, -1 plus 1, or I guess it's going to be +1, -1, 1 minus 1, 1 minus 1. I'm just going to keep, alternating back and forth. So I can say again by the nth term test, this is not equal to 0, so this diverges. Okay, so let's write down our interval. Doesn't include -3 and it doesn't include +1 for our endpoints. This is what you want to go back over and do on chapter 4, 5, and 4, 6 for those 4 problems. You're going to check the endpoints on the polynomial. Then on 4, 6, you're going to check the endpoints on the derivative of the polynomial and the integral of the polynomial, because they may change when you take the derivative and the integral. All right, so let's do example 7. All right, so example 7, x to the n all over n squared. We did our ratio test. Radius is 1, center is 0. -1 to 1 are our interval of convergence values. So let's check them out, see which ones, we kind of given ourselves clues here, but let's check. X equals 1, we'll do first. So wherever I see an x, I plug in a 1. Right? This is a p series. P is equal to 2, therefore this thing converges. So 1 is included in my interval. The bounds are included. X equals -1. Everywhere I see an x, I plug in a -1. N squared. This is an alternating series. See how you need to know all the different series tests so that you can recognize the series types and then work it from there. So I'm going to do my first check, and that goes to 0. 1 over n plus 1 squared is less than or equal to 1 over n squared. Check, so this thing converges. So my interval -1 to 1. Both numbers are included in the bounds. That's 4.5. I'll let you guys finish writing that, and then we'll take a look at 4.6. I think we'll do maybe one. I think I did one example. All right. Like I said, I'll scan these in later. So that's 4.5. 4.6. All right, so if I take a look at example 2. So what we did, we're going to do it piece by piece. So example 2, I've got find the radius and interval of our function, the derivative, and the integral. Okay. So what you need to remember is you only have to do the ratio test once. Do it on the function, because the radius, the center, and the numbers for your interval will be the same between your function, your derivative, and your integral. Don't repeat this for each new process that you're trying to do. You're going to waste a lot of time. The radius will be the same, and the center will be the same, and the numbers on the interval will be the same. It's just whether or not the endpoints will be included. So we have to do an endpoint check. Okay, so I'm going to check -1 and +1. So x equals -1. I'm going to plug in for this one here. So everywhere, we just did something like this. This is going to be -1 to the n all over n. This is an alternating series test. I think we just did this, so I'm not going to go through. This is going to converge. Okay, x equals +1. 1 to the n all over n. I think we just did this one. This is a p series. This diverges. So our interval, I have it written up here. Our interval is going to be, it includes -1, but it does not include +1. Okay, so we did an endpoint check on our function. Okay. So now when I do the derivative, okay, I have to. I don't have to do the ratio test anymore because my radius and my center are the same as before. My interval values are the same, but I have to do an endpoint check again. Okay, so let's check it. So x equals 1. We'll check that one first. So x equals 1. I'm going to plug it into here now. I'm not plugging it into my f. I'm plugging it into my f prime. This is my function right here. Okay, so I'm going to go n. Wherever I see an x, 1 to the n minus 1 all over n. So what am I doing? I'm summing up. N's cancel. I just get it equal to 1. 1 to the n minus 1 is just still 1. I'm summing up 1 plus 1 plus 1 plus 1. It's, you know what it's going to do. We'll just say by the nth term test, this thing diverges. Okay. X is equal to -1. N all over -1 to the n minus 1 all over n. This is going to be equal to, right, -1 to the n minus 1. So this is just going to go -1 plus 1, -1 plus 1, so on and so forth. Okay, which means by the nth term test, this diverges, which means that my interval is going to be -1 is not included, +1 is not included. That's different than my function, right? My function included -1, but not +1. See the same numbers, but it's not included. Okay. Okay, we're going to do our integral, right? We did the integral part before, but now we need to check the endpoint. So when we did our integral, we came up with a new series, right? X to the n plus 1 all over n plus 1 times n. So I've got my same values. X is equal to +1. We'll check. So everywhere I see an X, I plug in a 1. Okay, whoops, sorry, you can't see what I'm doing. Okay. This one here is going to end up being 1 all over n times n plus 1. I'm going to do a limit comparison with 1 over n squared, right? Because this is n squared plus n. So 1 over n squared is my dominant term. So this is a p series. It converges. right? Because p is equal to 2. Okay, when I do the limit comparison, right, I'm going to go 1 all over n plus 1 all over 1 over n squared. What am I going to get? N squared over 1. So this is going to basically be n squared over n squared. This comes out to be equal to 1. This is positive and finite, which means it converges also, because the thing that we're comparing it to converges. Okay. So my positive one is included. Let's do x equals -1. Oops, sorry. X equals, trying to get this all in the window here. X equals -1. So everywhere I see an x, I'm going to plug in -1. Right? So we have an alternating series. I'm going to do my check. So this is the limit as n goes to infinity and n plus 1. This is equal to 0. That's good. 2, I won't write it out, but I'll just say a sub n plus 1 is less than a sub n. It's good. So this thing converges too. Right? So then my interval is going to include both endpoints. Okay. So 4.6. You have to show your endpoint checks, all your series, the things that you've learned before. Okay. And then I think, yeah, my 9th grade class, my 9 o'clock class, we ended here. So that I think what we're going to do is tomorrow, we'll take tomorrow to finish up these examples for 4.6. Okay, so that you guys can, sorry, there you go. So that you guys can see 4.6, how that holds together. And then if you have any questions on homework problems for 5.3, 5.4, 4.5, 4.6, you can ask them also in class tomorrow, in case you can't make it to office hours. Okay. So why don't we do that? We'll keep it in time with the 9 o'clock class. So why don't we stop there? Okay, guys, how's everything going? It's a lot to take in. There's a lot of stuff. That's why
my page of notes is very full today.
Right? I know, I hear you. That's kind of why I want to give you guys a chance to let your brain absorb it all. But yeah, but make sure, you fill out the table. You now have the checklist for questions to ask. Which series test should I use? Okay, like I said, you probably want to maybe find an example, one of convergence and divergence, one for each of the series test, if it's possible. You're on your last sheet of notebook paper. I know. I've been burning through paper like mad, but that's part of what it means to be remote, right? But
it's good occupational therapy to get your hand moving.
It is. It's true, actually. That engages the motor cortex, right? So it's a good thing. I don't mind it. So that you have 100 pages of notes for this class alone. Is that? I believe it. I probably have about 150 pages of notes for this class too, but I go heavy on the examples so that you guys can see a lot of different stuff, and then get a feeling for how things work and what to do. Okay. All right, so let's call it a day for here. Okay, but come prepared tomorrow to finish up 4.6 for these examples. We're going to go back over all of our, I'm hoping it's 150 sides. Because it was 300 pages, then we're done. But anyway, so come prepared tomorrow to talk about the rest of this 4.6 and then to ask questions, okay, on 5.3, 5.4, 4.5, and 4.6. Okay. Okay, guys, have a great afternoon and let your brain decompress a little bit.
Thank you.
Bye, guys. Take it easy.
Thank you.
Take care. Bye-bye. The table of contents is a great idea.